The ratio test is another method for determining convergence and divergence in series. We have our series of a sub n, and what we're saying is that we take the limit as n approaches infinity of the absolute values of our a sub n plus 1 term, and we're dividing that by our a sub n term, and we're going to call that L. What the ratio test tells us is that if L is less than 1, our series converges. If L is greater than 1, our series diverges, and if L is equal to 1, well then the ratio test doesn't tell us much and we gotta perform a different test. So let's use this to solve a couple sample problems. So here we have our series, which is an infinite series from n equals 1 to infinity of n factorial over 9 to the n. And a lot of ratio test problems, you're going to be looking for factorials and exponent. If you see those, you're going to have to be thinking, well, maybe I should take a ratio test. So let's go ahead and do that. So remember, we're taking the limit of the a sub n plus 1 term and dividing that by the a sub n term, limit as n approaches infinity. So if we do that for this, we get the limit as n approaches infinity of, and this is going to be pretty much the only time you're going to see me writing this like this, but remember we're pulling in n plus 1 factorial, and that's over 9 to the n plus 1, and we're dividing that by the a sub n term, which is just n factorial over 9 to the n. And what I meant by before, but I'm not going to write this again, is just because this is equal to, when we're dividing by some fraction, it's the same as multiplying it by its reciprocal. So this is equivalent as the limit as n approaches infinity, n plus 1 factorial over 9 to the n plus 1. And we're going to multiply that by the reciprocal of this bottom part, which is 9 to the n over n factorial. And a lot of cool algebra canceling happens right now, and that's what's usually going to happen in these types of problems. Well, we have an n factorial on the bottom and an n plus 1 factorial on the top. Well, n factorial is just n times n minus 1 times n minus 2. And n plus 1 factorial is the same thing as n factorial multiplied just by one more n plus 1. So if we rewrite that, we can see that all we're left with from the factorial is just an n plus 1 on top. It's just, it's the absolute value of n plus 1 on top. Now let's see what happens with the 9. Well, on top we have a 9 to the n, and we're dividing that by 9 to the n plus 1, so basically we're just dividing it one more time by 9. So all this is going to cancel out with that, and we're just left with the 9 on the bottom. So we have the limit as n approaches infinity of n plus 1 over 9. And here, now that we simplified that, we can take the limit, and we just get infinity plus 1 over 9, and that's just going to be infinity. Infinity is indeed greater than 1, so our series diverges. Now let's look at a bit of a trickier problem. And once again, you guys can pause the video and try this out and then come back when you guys are ready. So we have the series from n equals 1 to infinity of 2 to the n over negative 3 to the n plus 1 times n. So remember, we're taking the limit as n approaches infinity, and I'm just going to go ahead and write it already using the reciprocal. So we take the n plus 1 term, so that'll give us a 2 to the n plus 1 all over negative 3 to to the n plus 1 plus 1, because we already have an n plus 1 and we're adding another one, multiplied by n plus 1, and that comes from this little n right here. Now we're going to take the reciprocal and we're just going to keep it as n, not n plus 1, so we get on top a negative 3 to the n plus 1 times n all over 2 to the n. And once again, you can see some cool algebra happening right here. This 2 to the n cancels out with this power, and we're left with a 2 on top. And also this negative 3 to the n plus 1 plus 1, well, that's just negative 3 to the n plus 2, and this is negative 3 to the n plus 1, so our denominator has one more negative 3's. So all of this is going to cancel with all of that, and we're left with a negative 3 on the bottom. This n over n plus 1, we can't really do anything about that yet. So if we simplify that, remember, we can limit as n approaches infinity if the absolute value of, well, we were left with a 2 on top and a negative 3 on bottom. And then we're left with an n over n plus 1. And from here, you can, one thing you could do if this makes it easier for you to see is, well, 2 over negative 3, that's just a constant. If it makes it easier for you to see this, you can just pull that out, and remember that we're taking the absolute value, so we drop the negative sign, and then we have the limit as n approaches infinity, the absolute value of n over n plus 1. And when you have the same power of n on both the denominator and the numerator, then we're just going to look at the ratio of its coefficients. In this case, the coefficients are 1 and 1. So all of this is just going to equal 1. You can also show that doing L'Hopital's, and you take the derivative of n and you get 1, and the derivative of n plus 1 is also 1. But basically, then that will equal, well, just this 2/3 over here. 2/3 is less than 1. So our series, well, if it's less than 1, it will converge. And that's the ratio test.